Welcome everyone back to the second lecture by Camillo. And today he's going to tell us about harmonic multivalued functions.
Okay, very well. So does that mean something? Okay, perfect. Yeah. So after the introductory lecture, let me this time just go directly to the meat. So I'm going to assume today now that T is an integral current, which means I am in the situation referring to the lecture that I gave in Tuesday, that the coefficient group is actually given by Z. Okay, so what I call the coefficient group of my current is Z. Very well. So it is an integral current, area minimizing. And we are in codimension bigger or equal than 2. So not only that, somehow let me fix, say, some open set U, which is far away from the boundary of this current. So that all I actually care about is really the interior minimum, the interior regularity property. Okay, so you intersected what normally is called the support of the boundary of your current is equal to 0. Okay, is equal to the empty set. Okay, so now remember what was the enemy. So the enemy was the following situation. So so we know that. So first of all, we know that in a generalized sense, on a large subset, so on a very large subset, there is a flat tangent. Okay, and by this flat tangent, I mean that in some weak sense, at a sufficiently small scale, your current is sufficiently close to be a multiple copy of a plane. The only problem is that there is this multiple in front of the copy of the plane. So if the multiple were exactly equal to 1, then you would apply classical theory to conclude that the point is regular, but the multiple we discovered can actually be more than 1, and you can have all sorts of singularities which still have a flat tangent. Okay, so the pivotal example is the following. So by a theorem by Federer, so any complex holomorphic variety in some complex space, which I'm going to identify with a two n-dimensional Euclidean space, is area minimizing. Okay, so this in particular gives us two examples which are going to guide our intuition of how our flat singular points can actually look like, which are the enemies, and which I want to show. I can't show that the flat singular points are absent, but what I want to show is that there's a limited there is a limited number of them. Okay, and so the pivotal examples that I want to consider are situations like this. So first of all, maybe some complex curve which is of the following type. Let me just put, like, I don't know, Q and Q plus 1 over here. So that's one pivotal example. But there's another example, which is just a small variation of this. And the small variation of this is going to be so the small variation of this is going to be, okay, so let me think about that. Yes, okay, so the way I want to write it is something like this. So z plus, I don't know, some holomorphic function phi of omega. And now here I have the power q, and here I have the power w to the q plus 1. Right, and actually, let me just put even an integer k over here in front. Okay. So let me highlight the difference now with this example is that here I have some other function phi, which is holomorphic. Okay, so this is holomorphic. Okay, so these are the two key examples. And well, the first thing that I just want to recall is why. So why do we have regularity in the lucky case? Okay, and remember, the lucky case is the situation in which my flat tangent actually happens with multiplicity 1. So I don't have this higher multiplicity, which which occur when I have these branching singularities. Well, this is an idea which goes back to de Giorgi. And the idea is simply the following. So roughly, when the flat tangent has multiplicity 1, at small scales, the current is close to graphical. Oops, this was very bad. Okay, so what do I mean by this? Well, I mean, now we don't yet know that the thing is graphical, right? So we don't yet know that the thing is graphical because that's actually one of the things that we want to prove. But let's say maybe the surface look like this. And a priori, there might be some little protruding portions over which maybe I'm folding the surface, and so I can't really say that the surface is graphical. But since I'm actually taking this, since I'm actually close to this plane over here with multiplicity 1, a simple measure theoretic argument actually is going to tell you that if I look at my base plane down here, so there's a very large set on my base plane. So let me call this set omega. And this large set is in the measure theoretic sense. So most of the points on the plane actually are covered by this omega. So that on top of this region omega, I'm only seeing one single point in the support of the current. So say if on a very large measure, I see 2 points lying on top of the current, then I'm closer to 2 copies of the plane than I am actually to being close to 1 copy of the plane. Intuitively, this is what is happening. Okay. So now this does not tell you that you are fully graphical, but it tells you that at least on a large portion, your current can be very well approximated with a graph. Okay. So if the current were a graph, okay, so if the current were a graph, then the volume or the area of the graph would be given by the following formula. So over the graphical region omega, you would have the square root, and then here you would have 1 plus modulus of gradient of f squared, and then you have the sum for k, which goes to 2 to the dimension m, and then here you would have okay, so let me not actually be so precise. Let me just say you have the sum over all k times k minus m with k bigger or equal than 2, and here you would have the determinant of this minor m to the power 2. Okay, and these are minors inside my matrix DF. Okay, so now you notice something interesting in this, and what you actually notice is that if I make a Taylor expansion, so this term over here is almost, or is certainly at least quartic. Okay, this one over here is quadratic, and when I am actually very close to be a tangent plane, I can imagine that my function f, of which I am a graph, at least on a very large portion of the domain, must have a very small gradient. After all, if the function f were like C1, having a flat tangent and having actually taken the tangent at the point 0 to be horizontal means that the modulus of gradient of f is actually very close to be 0. Okay, so this means that I can make a Taylor expansion, and I can write my area functional as a constant 1, which is of course irrelevant for the minimization property, and then I have the Dirichlet energy, and then I have higher order terms. Okay, just remember that there is this 4 over here, because at a certain point it will be actually useful to remember in my discussion. Okay, that being the case, you can imagine that your current must be close to the graph of an harmonic function. Okay, and since it is actually close to the graph of an harmonic function, well, harmonic functions have very good properties, decays of the integral norms, and it is possible to transfer these decay of the integral norms at the nonlinear level to the current if you actually look at the appropriate quantities. And these decay properties gives you a C1 alpha regularity. Okay, so the George's idea is, so show appropriate decay properties of some integral quantity. And just to give you an idea of what this integral quantity is, I mean, the quantity that looks actually natural to look at is what is called the excess. I mean, there are other quantities that you can actually look at, but the quantity that he looks at in his original paper is called the excess. Now, in the simple situation in which you are a graph over a cylinder, the excess is the difference between the area of the surface of the graph, or the area of the surface of the current, if like somehow the surface is making folds, minus the area of the cross section. So it's like area of the like red region, okay, minus the area of the basis of the cylinder. Okay, and when you go actually back to this formula over here, if you're looking at the excess, you just mean that you are subtracting the basis of the cylinder, so the area of your domain, which means that in this expression it's as if you are actually subtracting 1. Right? So the quantity that you're looking at, which is called the excess, looks roughly like the integral of modulus of df squared. Okay. Now, what happens if you look at a quantity which is slightly different? So what happens if instead of looking at what happens if instead of looking at like, you know, that difference, you just make a slightly tilted, you just take a slightly tilted intersection of the cylinder with a plane which is a bit tilted, so something like this. Okay, and assume that your cross section is the graph. Okay, so now this is a bit more delicate computation, but once you actually look at the same quantity over here, so if you look now at area of sigma minus the area of this tilted, now it's not going to be any more like, you know, a disk, it's going to be an ellipse. So let me call it E. So let me call this E. So this guy looks like something which is very nice, which is the integral of the values of the f, and then you have to actually subtract the linear function which is parameterizing your plane over here, right? So this plane. Okay, so now why is this very interesting? Well, this is very interesting because if you minimize over all possible planes this quantity, so you actually minimize L, right? If you were a graph of a function f, you would in fact know that this minimum I'm getting ahead of myself over all linear L, and say if I do it on the ball of radius r, okay, this minimum is actually achieved by the average of the derivative of f on that ball. Okay, and what is very nice about this is that if you are harmonic, so if you were harmonic, so f is not exactly harmonic, but if you were harmonic, this quantity over here decays. So for harmonic function, you actually have the following simple estimate, which is coming from, well, elementary properties of the harmonic function. So this quantity over here is less or equal than a constant times r squared. Okay. Now, what is this actually? This is a kind of Morrey estimate on the oscillation, on the L2 oscillation of your function gradient of f. So of course, harmonic functions are extremely regular. So you know right away that they are regular, they are real analytic. You don't need actually to use Morrey's estimate. But Morrey's estimate would tell you immediately that if you have a function which satisfies this decay, then the function is actually C1 alpha. So this is, say, Morrey's lemma, right? So if you have a function such that the average over the ball of radius x of, say, g minus the average of g over the same ball as an estimate of the type constant r to the 2 alpha for every x and r in reasonably, then g is actually C0 alpha. Okay, and if you actually have something like that at the level of the derivatives, then from this, what you're actually getting is that f is C1 alpha. Okay, so now the idea is that since your current was almost harmonic, you could actually lift this property, this decay quantity, for which you can, I mean, for which you have to find a correct sort of geometric interpretation in the case of a current, which is not exactly the graph of a function. But if you can prove an analogous estimate over here, then you can use a geometric version of this Morrey's lemma on the currents to actually show that your current is C1 alpha. Okay. And so where are you using? So where are you using sort of the fact that you start off at a certain scale sufficiently close to the plane? Well, it's because your current is not exactly harmonic, right? So it's not exactly the graph of an harmonic function. It's more like weakly harmonic, or like close to be weakly harmonic. But in fact, if it were the graph of a function, that function would satisfy an elliptic system of ODE, of PDEs, which is the elliptic system of the minima surface problem. And that one is close to be the Laplace equation when the gradient of f is close to be, I mean, when the modulus of the gradient of f is sufficiently small, essentially. That is the idea. So this is the upshot for the De Giorgi case. Now, what happens, I mean, what does go wrong when you actually look at your situation in which your current looks like, for instance, this z to the power q is equal to w to the power q plus 1, right? I mean, now what is happening is that on top of each point over here, you're actually seeing every time q points, right? So if this is a point, say 0, w, right? On top of here, you just have many values. In fact, q, right? So each of these points is given by zw, where z to the q is equal to your w to the power q plus 1. And since you are in complex coordinates that are exactly, as long as you stay away from the origin, in which you have only one point, as long as you stay away from the origin, you're actually looking at least q points, okay? At exactly q points. And well, if you follow, say, a radial direction towards the origin, these guys, they might actually form q nice functions, but when you are looping around, right, so there will be I mean, the loop will not trivially close, so you will not actually come back to your red point you started with, then you're actually starting winding around at different points. And then sooner or later, you actually start where you go back. So you have a complicated surface, which is a Q cover of your plane. You can't say that you are a single valued function, but actually in this example, what you can obviously say is that you are a multiple valued function, okay? So the idea of Almgren is at singular points, okay, you can, so at singular flat points, you can at least approximate with a multivalued function. In fact, not only you can approximate with a multivalued function, but so you can also decide on how many values. So we use this like number q. So here for the q values, where this q can be identified. So this number is the multiplicity of the plane you're close to. Okay, so now, even though you are a multi-valued function, of course, you're still very far from, I mean, you can't hope for, say, some regularity like the one you got from De Giorgi's theorem. So a first naive attempt would be actually just to show some sort of excess decay by just saying, okay, even in this case, I can look at the total volume of the surface inside a cylinder and subtract q copies of my base and trying to prove that if I am, if this excess, I mean, if this quantity is sufficiently small, then it starts decaying. Okay, so an excess decay is actually false. You can make counterexample to this. So beware. So in excess decay in this setting is false, even if you find the correct multivalued analog. So even if you state the multivalued analog of the George. Okay, so in this case, you cannot actually use that approach. Nonetheless, let us look at what you can do. So one thing that you can, one thing that you can hope for is, so first of all, you can hope for a, so you can hope for the existence of a robust theory of multifunctions which minimize the correct analog of the Dirichlet energy. Okay, so in order to do this, you would have to define, say, a subole space of functions, which is in W12, which takes more than one value. It takes, I mean, these like Q fixed values that you started with. You want to define the correct Dirichlet energy, and beware, it's not like it's not like you are really allowed to take any abstract definition of Dirichlet energy. You have to take the Dirichlet energy, which comes from the linearization of the area functional. And this multivalued graph, if it is a current, it has a very well-defined geometric volume, which you cannot tweak. So it's not like you can try any type of generalization of the Dirichlet energy in this kind of setting. I mean, it's the data is given to you by the geometry, because this Dirichlet energy has to be like the linearization of the area function. Okay, so now this robust theory actually exists, and I mean, it was done back in the 80s by, or actually in the 70s by Almgren with a very hands-on approach. But what we have in the papers with Emanuele Spadaro is a kind of modern point of view on that, in which we are using tools from metric geometry to make our life as easy as possible. What is the most interesting point, though, is how do you get regularity for these minimizers? I mean, the existence is kind of soft theory, or like, you know, generalized functional analysis, and we have lots of tools to do. So how do you actually show regularity for these objects? So how do you show regularity for these objects? So one of the important points that does not allow you to apply many of the powerful theories that you have for harmonic functions is that, unlike the single valued situation, this situation over here does not give you a linear space. So what is going to happen is that in this multivalued setting, I don't have, I mean, like, okay, so this picture is kind of deceiving, because in this picture, which, you know, I can only picture something which is three-dimensional. So the codimension that I'm actually drawing over there is 1. And what is happening is that if you have codimension 1, you can always order your sheets, because the target of your multivalued function is R. And I can always order the sheets from, like, you know, top to bottom. From you give me Q points, and I can always order them from the smallest one to the highest one. Okay, and that sort of gives me a decomposition of my multivalued function into single valued functions, which is very very comfortable thing to do. But in the higher codimension, I cannot do that. I mean, there is no way of breaking this function over here as the union of Q-valued single functions, which are also kind of smooth, right? So I can break it into pieces, but if I break it into pieces, I actually have to introduce discontinuities. So I can't break easily that object over there into a bunch of single-valued harmonic functions. So in particular, what I really lack in this space of multi-valued functions is I lack linearity. So note that we do not have linearity, meaning there is a very well-defined notion of multiplying my multi-valued function by a constant, by a scalar function, actually, right? So because I can take every value and I can magnify every value by the same lambda. But what I cannot do is I cannot sum two different q-valued functions, because to sum the values, I actually need to decide an order for them. I need to decide which value is summed to which other value. And deciding for an order is exactly what I don't know how to do in this setting. Okay. There is, however, something which is extremely robust. And there is this, which was like a great discovery. But then I learned actually not so long ago by giving a talk in Jerusalem. It's actually a rediscovery. So Almgren rediscovered the monotonicity of a very interesting quantity called frequency function. And this quantity actually reads like this. So it's the integral of the Dirichlet energy on a ball of radius r centered at x, and it's divided by the integral over the sphere of modulus of u squared. Okay, so this quantity for an harmonic function is monotone increasing. So let me just say this one for a classical harmonic function is an exercise. It's not a simple exercise though. It's a kind of interesting exercise. So for an harmonic function, this quantity is monotone and since it is monotone, you can now just make the same procedure that we did for the case of integral area minimizing current, where we had another monotonicity formula. We just took rescalings and then we took limits of rescalings. So this means this monotonicity actually tells you that limits of appropriate rescalings in which I am zooming into a point converge to a tangent function for which the frequency function is actually constant. So let me call this tangent function, say, u0. And for this u0, you have this property. Okay, well, why now is this wonderful? Well, because the monotonicity formula actually comes with a characterization of the functions for which this happens. Okay, so this actually happens. So let me call it 1. So 1 happens if and only if this quantity over here, which I could call I0. So this happens if and only if U0 is I0 homogeneous. Okay. So now, first of all, this monotonicity, so the monotonicity is very robust. Meaning that you can actually prove it even for multi-valued minimizing function. And the reason why it is actually very robust, it's because it depends on two identities, on two variational identities, which in the classical case, you can derive by being a solution of Laplacian of u equals 0. But for which you actually don't need the PDE to derive it. So the monotonicity is very robust, and it comes from two identities. So one is the variation of the domain. So I can always compose my function with a diffeomorphism of the domain to find a new competitor, if the diffeomorphism actually keeps the boundary value fixed. So this one, let's say it's what we call internal variation. So we take a one parameter family of diffeomorphisms and we compose our function with it, and then differentiate at time t equals 0. And if you are a minimizer, then you have to be stationary for this. And the other identity is stationarity with respect to composition of diffeomorphisms of the ambient, which you could actually call external variation. Okay, any one parameter family. And what is actually very nice is that both operations are in fact geometric, right? So if you have a multi-valued function, you know that for each point in your domain, you attach q values. If you're composing your domain with the diffeomorphism of itself, you still have this property. I mean, you still keep this multi-valued function. And at the same time, if your multi-valued function is taking values in a certain target, if I compose my target with the diffeomorphism of it onto itself, I still keep actually being q-valued. So the big thing of these two identities over here is that I don't need the linear structure of my space of competitors to actually be able to compute these variations. Okay, so 2 and 3 are independent of the linear structure of the classical W12 of omega taking values, say, in some R, okay, or in some Rn. It does not depend on the linear structure. And so you can actually do it for you can actually do it for the for these guys, for the multiple valued functions. And what is actually the big deal now of this? Well, the big deal is that at every point where you might be singular, you actually have a tangent function attached to it. Well, you don't know the tangent function is unique. That is in fact unique in 2 dimensions, but that is an interesting problem per se. But what is interesting is that this tangent function being homogeneous in the radial variable, it has actually become a simpler function, right? So if you think, for instance, that you started with the PDE, which therefore is on a function which depends on 2 variables, if I actually tell you that this function is radially homogeneous, then it immediately becomes actually an ODE problem. Okay, so now here there's something which is not so difficult to find out. So if the domain is 2-dimensional, and your multivalued harmonic function is radially homogeneous, okay, then either it is regular, or the origin is an isolated singularity. Okay, in fact, it's much better than this. So in fact, what you can actually show with a little bit more effort is that this first example here, this first example one, where instead of having q and q plus 1, I substitute q and q plus 1 with, you know, general guys. Like say here, like say some p, and here some q. Well, these examples are in fact essentially a classification of all possible harmonic multivalued function on a two-dimensional domain, which is singular at the origin, meaning that up to rotation, translations, and, you know, identification of some complex structure, I can essentially break my homogeneous dir minimizer in two dimension into a superposition of finitely many of simple pieces like this. So you really have a complete classification of this. Okay, so this suggests you a way of showing that singularities for the initial problems for the dir minimizing q-valued functions before you actually make the rescaling procedure, since the tangent function has an isolated singularity, you actually hope to show that your graph is in a neighborhood of your singular point, diffeomorphic or maybe homeomorphic, or, you know, more or less so similar to your tangent function, that in fact at a sufficiently small scale you will only see the central singular point and you will be regular anywhere else. Okay, so, and you can do this. So you can use these ideas to prove that harmonic multivalued functions on two-dimensional domains have isolated singularities. Okay, so the trick to do this, so there is one important ingredient still missing in this picture. And it is what actually in our papers we call persistence of singularities. And this persistence of singularities is something like if I actually have a singular point for my dir minimizing function and I rescale around this point, this singular point will actually be inherited by my tangent function too. Okay, so now the point is that this persistence of singularities is actually quite delicate. So you need to do it. So you need to mod out all the regular part to hope for this. Okay, so what do I exactly mean by that? Okay, so there is an analogous of Federer theorem, which actually tells you that an holomorphic subvariety is not only giving you an area minimizing current, well, by intersection properties of holomorphic subvarieties, and holomorphic subvarieties which is close to a plane is always going to be a multiple cover of that plane for a fixed multiple. And once you write it as a multivalued function, it's also a dir minimizing function. So holomorphic subvarieties gives you at the same time area minimizing currents and harmonic multivalued functions. So it's a quite curious phenomena, but I mean, it happens also at the level of a single valued function. So if I take a single valued holomorphic function from C to C, the graph of this single valued function is at the same time an area minimizing surface, so it solves the minima surface system, and it is at the same time harmonic. Okay, and the reason, like, you know, in two dimension, you can actually draw this back to notions like, you know, conformality and harmonicity and so on. Okay, so let me therefore take the example 2. Right, so if you remember the example 2, this was something like this. So my function was z minus phi of w to the power k. Okay, and then over here I had, well, actually I had q. Okay, and then let me just say here I have some w to the power p, and let me just assume that, you know, the greatest common divisor between q and p is equal to 1. Okay, now what is this function phi of w? So this function phi of w might be any holomorphic function, right? So this might be, for instance, phi of w, which is going to be equal to, I don't know, some coefficient a0 times w plus, I don't know, some other coefficient a1 plus w squared and so on. Okay, so now ideally, what I would like to do is I would like to write z as a function of w, and what does it look like? So z looks like, you know, a0 of w, which is single valued, plus a1 of w squared, which is single valued, and then somewhere over here, I'm just going to put this w to the power p over q. Okay, so quote unquote, right? So because I have to take a determination of my q root, but locally this is what I'm going to see. Okay, so now this p over q, okay, in our example, it was actually k q plus 1 divided by q, right? It's going to be like k plus 1 over q. And although it has this singularity over here, notice that this k might be very, 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 very large. So in this kind of Taylor expansion that I'm having over here, I don't know how big is this in terms of homogeneity with respect to, for instance, this guy or that guy. Okay, so therefore, if I'm actually going to take the graph of this function, which I actually call f of w, okay, so if I'm going to call that function f of w, what I potentially see is something like this. So here I have my first approximation, which is a linear function. Then maybe I have my second approximation, which is a parabola. Okay, so let me say this one is a0w plus a1w squared. And then I have a branching on top of this because I have these q roots, right? But these branching are maybe tiny, tiny perturbations. Okay, now when I zoom in, when I make actually my picture smaller and smaller, if I want to find something meaningful, of course, I'm rescaling the horizontal coordinate by a certain factor, right? So I take this segment and I magnify it. But then if I want to see something meaningful, I have to magnify by a factor over here so that sort of this quantity gets rescaled into something which is at scale 1. Okay, and once I do this, I'm going to see something like this. But then whether I see something multivalued or not in the limit depends on the relative size between this difference and this difference, right? So if the ratio of red over blue is going to 0, in other words, if my p over q is bigger than this thing, my p over q is actually bigger than 2, well, in this case, actually, what I'm going to see really is a flat tangent, actually. So in this case, what I'm going to see is really 1. So if P over Q is bigger than 1, when I actually rescale this picture, what I'm really going to see in the limit is just this flat line. I'm just going to see this guy. Okay. So if I want to see something meaningful in my rescalings, what I need to do is I need to subtract the regular part, and in particular, or the regular part, before I actually see the singularity as my first homogeneous part of the function, which is, I mean, as the largest homogeneous part of the function in this expansion, right? So if I see some homogeneous part which has homogeneity, which is lower than the homogeneity of my singular behavior, my tangent function is not going to capture the singularity in the limit. Okay? So I need a way of subtracting this core, this phi of W, which is regular. Okay? So how do I actually capture phi of W? Well, in the case of harmonic functions, there is a very simple way of doing this. So this phi of W in the example which I just told you, so phi of W is actually equal to the average of the sheets. In other words, what I'm just saying is that take your multivalued function, right, which on top of each point takes Q values. And for each of these guys, calculate the body center. Okay, so calculate the body center over here. So this is the body center of the red dots. Okay, and now do this over all your domain. And the body center is a single valued function. Okay, so now what you can prove is the following simple lemma. So the body center gives you a classical harmonic function. Okay, you take this classical harmonic function. This is exactly this phi of W in this example. So you capture this phi of W without knowing a priori the regularity. I mean, in this example, you know all the regularity that you want because you're actually an homomorphic curve. But in general, you don't. What I'm just telling you is that even if you don't, just take the average of all the sheets, that's harmonic, and take it away, because now I can't subtract a multivalued function from another multivalued function, but I can subtract one single valued function from a multivalued function. So because at each fixed point where I calculate the Q values, I'm subtracting the same for all of the Q values. So I don't need to order them in any way, okay? So once you subtract this body center, this time the singularity is robust. You make the rescaling and you will actually capture the singular behavior. So the singularity becomes robust. Or if you want, stable under this rescaling procedure. Okay, and then you can carry on all of this analysis. Okay, so now what is actually, so I've just told you what happens in the situation in which you have an area minimizing current and the coefficient group is actually Z. What happens in all the other cases that I told you, when you are at the boundary or when your coefficients groups is actually G and so on. So what happens is that for each of these situations, you can actually cook up a concept of harmonic approximation. And this concept of harmonic approximation actually is different from case to case, okay? But what you can show in all of the situations which I told you is that there is at least a surrogate of this frequency function. You can build up a theory for, W12, so you can build up an existence theory. There is a surrogate for this frequency function. There is a surrogate for these two variational identities. You can actually then define tangent functions. And in all of these situations which are linear, there's also a surrogate for the average of the sheets. And once you subtract it, you actually have this persistence of singularity. So this tells you somehow that in all of these situations, you can construct a linear theory, and the linear theory has a very similar regularity theory as you're hoping to have for the nonlinear theory. So the linear objects are not regular, but the set of singularities have a bound on the Hausdorff dimension, which is actually the expected bound on the Hausdorff dimension for the nonlinear problem. Okay, and so this is actually the end of my lecture. So I gave you sort of a rough picture of what goes on. And what I will try to explain you tomorrow is how you actually try to make this linear regularity theory, how you actually can try to transport this linear regularity theory to the nonlinear setting of area minimizing couplets. Okay, thank you for your attention.
Thank you, Camillo.